Hey everyone, in this video we're going to talk about linear approximation. It's just another little application of derivatives that you're going to find in this chapter. And so this one's kind of interesting. This will be a relatively short video, but it kind of is an introduction to something you're going to do in much more detail when you get to Calc 2 and you learn something called a Taylor series. But for now, this is a very brief introduction, and it's going to seem ridiculously simplistic in this sense. You have to kind of suspend reality for a little bit and pretend you live in a world where you only have four calculators with four operations: addition, subtraction, multiplication, division. Because if you do that, then you'll understand why we're doing this. Well, you won't understand why we're doing this, because anything we do here, we can just plug into a calculator to get an answer. But let's forget that for a minute. All right, linear approximation. Let's start with a very basic function. Here's my f of x function. And from there, I'm going to find some a value somewhere that I know I can draw a tangent line directly at a. And when I plug a into my function, of course, I will get f of a. So I have a and f of a. The idea behind linear approximation is we can actually utilize the tangent line to approximate a value of our function that's close to a known value a. In other words, if I know a and I know what f of a is, I can pick any value x that is somewhere close to a and doesn't, relatively close. Let's, I'll do a little x over here for a second. There, I'll put my x there. And it comes from this idea that if you wanted to get the x value here, but you couldn't plug x into your function, you could actually utilize what x is from the tangent line, because those values are close. Remember, this is just an approximation. All right, so why would we do that, and how would we do that? Well, to get started, let's just develop a very simplistic equation of a line for our tangent line using our a value. So in other words, we know that to develop any equation of a line, you can use ry minus y sub 1 equals m times x minus x sub 1. And that is our point slope formula. To do a point slope formula, you of course need a point and you need a slope. So let's look at this tangent line I have here in red. The point, of course, we're going to use is a comma f of a. Well, the tangent line we are going to get from the derivative of f of x. So the tangent line, the slope is going to come from the derivative of f of x, but we want a numerical value of that derivative directly at a, so it's actually f prime of a. So we're going to use that slope and that point to plug into our point slope formula. And of course, that will give us y minus y sub 1 is f of a, the y value, the point we're interested in. Our slope is f prime of a times x minus a. A is the x value of the point. All right, we'll do a little rearranging and say that, hey, y equals f of a, because I can move f of a to the other side, it's positive, plus f prime of a times x minus a. And instead of calling that y, we're actually going to call this a function. We're going to call it our linear approximation function. And this is the linear approximation to f at a. or 2f, let's say, near x equaling a. Okay, so we would use this formula to approximate any x value as long as that x value is near a. All right, so we have our formula. Based on the graph I gave you, let's start with a function that makes sense, and let's use the square root of x. All right, so I would want to use the square root of x function to, let's use that and we're going to use it to approximate the square root of 24. All right, so what we're going to do is we're going to just get an approximate value for the square root of 24. Kind of simple enough. You will be given this. You will be asked to use linear approximation to approximate some value, in this case the square root of 24. The first thing you have to do is come up with a function that makes sense. In this case, of course, f of x equaling square root of x is the function that makes sense. But then you also have to think about, well, what is that value that is really near 24 that I can just do pretty much in my head? I can plug in, yes. So of course I can plug in, right, 25, and I know that the square root of 25, f of a, equals 5. I didn't need a calculator for that. So that's the idea. Do something you don't need that calculator for, and let that be your a. Your function is going to pretty much come from what you are given. Okay, so instead of square root, we're going to do a function of square root of x. Our x value itself that we eventually want to approximate, of course, is the 24. All right, so we have our linear approximation function that we now know, and if you don't remember it, it's pretty easy to get it. You're basically just using the equation of a line, equation of the tangent line. So we start with f of a. F of a we found to the side to be 5. So, we need the derivative. So we have our function, but now we need f prime of x. So if our function is x to the 1/2 power, we've done this one probably a number of times. You know that this is going to be 1 over 2 radical x. The 1/2 goes out front, x goes down to -1/2, which puts it radical x in the denominator. And we need more specifically, the 25. So we have 1 over 2 radical 25. Again, another thing you can do without a calculator. It's just going to be 1/10, right? 1 over 2 times 5, 1/10. Okay, so f prime of a is 1/10. X minus our a was 25. You're approximating x. We know our x is 24. We want to approximate what's a radical 24. So 24 is what gets plugged in for x in this case. And just do your math. So it's basically 5 minus 1/10, 5 minus 0.1, which is 4.9. And I'm going to change that equal to sign because this is, of course, an approximation. So L of 24 is approximately 4.9. All right, which means we can approximate square root of 24 to get 4.9. And you can plug that into your calculator and check your answer, of course. All right, and this can be done with any function. So for example, if you wanted to approximate, use linear approximation to get, let's just do sine of 89. I'll keep it in degrees and make it simple. Same thing, same idea, all right? Your function, your f of x, is just going to be sine of x, all right? Your x, of course, is the 89. Your a value is, you need, well, obviously the degree that is really close to 89 that you should be able to kind of think about off the top of your head is sine of 90 degrees. So you can use a equaling 90 degrees. F of a. And if you real quick just think of your sine curve, or remember your unit circle, you will recall that sine of 90 degrees is simply equal to 1. Okay? Well, now we need a derivative of x. Well, that's just going to be, cosine of x. Plug in your 90 degrees again. Now, cosine of 90 degrees is actually 0. So again, you should know, again, the easiest way I usually do it is I think of just the curve, the cosine curve. You know, this is 180 here, there's 360, so there's 90, it's occurring, and it equals 0. And just plug it into your function now. So L of 89 is going to be equal to, so there's your function, f of a plus f prime of a. So f of a is 1. F prime of a is 0, so it really doesn't matter that we're putting here, but you would have 89 minus 90. And yeah, this is a very simplistic problem, but it just simply comes out to 1. Because this sine of 89 is, if you plug it into your calculator, make sure your calculator's in degrees, not in radians, you will get 0.999999. So yes, we could say that sine of 89 degrees is approximately equal to 1. So again, simplistic because you can just plug these values into your calculator. But what's going to happen is this formula for linear approximation, you're going to actually expand on this and it will become something called the Taylor series. That it then becomes very useful because when you're working with Taylor series in the second half of Calc 2, you get to do things where you can use a polynomial to approximate a trig function. And as you all know, working with polynomials is so much easier than working with our trig functions or our natural log functions. So we'll expand on linear approximation in Calc 2, and then you can kind of approximate more complex functions using a more basic polynomial function. But this is just the first step of it. Okay, thank you.